Division of polynomials and the remainder and factor theorem. Let's start by defining what a polynomial is. A polynomial function of degree n is a function that can be written of this form. This writing looks a little technical. Let me try to explain it just using simple terms. So a polynomial function is any function that can be written as a finite sum. So you see here I have a bunch of sums of terms. This is one of the terms, this is another, and so on, right? So it's a finite sum of terms, each of which looks like a constant times x to some power, where this power is an integer that's greater than or equal to 0. It's a non-negative integer. So again, it's a finite sum of terms that look like constant. All of these guys are constants. I mean, you can read the next part. All these AIs are constant. They are real numbers. So these are real numbers. Okay. So all of these are real numbers, which means they are constants. And the x part is gonna have an exponent. They're gonna have an exponent. The exponent here is 1, right? So technically I can write 1. So in this case the exponent is 1, and over here it looks like I don't have an x, but the convention is there is an x to power 0. X to power 0 by convention in this section is equal to 1. So this guy is equal to 1, and hence the power is 0. Okay? So what's a polynomial function? It's a function that looks like a finite sum of terms, each of which looks like a constant times x to a power, where this power is an integer that's non-zero. For example, in this case, it's 0, and this one is 1, and so on, until you get to some number. The highest number, the highest exponent, the highest integer that sits on the exponent is called the degree of the polynomial. In this case, n is supposed to be the largest one. Okay? Because as you see, this is of degree n, so the power is n, and then it's decreasing. So the next one is n minus 1, so certainly it's smaller than n, and so on and so forth, all the way until you get to 0. Okay? You cannot drop below 0. That's the assumption here. The exponent is at least 0, and it's integer otherwise. Okay? So so this is what a polynomial is. Let's take we've seen many polynomials before. I'll take more examples below, but let me just put it in perspective. For example, I can think about a polynomial. Let's take it to be, we call it f of x. Polynomial function, an example can be a 5x plus 3, for example. 5x plus 3. It's a finite sum, so it's a sum of two entities, 1, 2, and each one of them looks like a constant times x to some integer, which is at least 0. For example, here the constant part, for this term, the constant part is 5, and the exponent is 1. Correct? And 1 is clearly an integer bigger than or equal to 0. For this guy, the constant is 3, and as we just discussed, this is x to power 0 here. That's the 1 guy, right? 3 times 1 remains 3. So the exponent for this term is 0, and the constant is 3. So all these functions, which were called linear functions, are polynomials. Okay? We've also seen polynomials of degree 2. This is, by the way, of degree 1 here, because the highest power between 0 and 1 is 1, certainly, right? So this is a polynomial of degree 1. Let's take another one, g of x, let's say minus x squared plus 3x plus 5. This is a polynomial as well. It's a finite sum of terms, each of which looks like constant times x to power, where this power is an integer greater than or equal to 0. Correct? For example, for this term, the coefficient, that constant part is negative 1, and the power is 2. For this guy, the constant is 3 and the power is 1, right? The power is 1 here. And for this guy, for the 5, remember the 5 can be thought of as 5 times x to power 0. So certainly this term looks like a constant times x to some integer which is at least 0. In this case it's actually 0, and the constant is 5. So this is a finite sum. It's a sum of 3 entities where each of them looks like this, and hence this is a polynomial. Okay, and this was called quadratic function. So quadratic functions are polynomials of degree 2 because the highest power is 2. Okay, so polynomials are actually generalization of numbers, because every number, every constant is itself a polynomial, correct? If I give you a function that looks like this, let's call it h of x equals, I don't know, like 7. This is a polynomial. Why? Because I can think about 7 as 7 times x to power 0. So isn't that a finite sum? Yeah, it's a sum of one thing, so it's itself. And doesn't it look like a constant times x to power something where this thing is an integer greater than or equal to 0? Yeah, it looks like a constant times x to power an integer greater than or equal to 0. So it's actually 0 in this case. So which means that 7 is a polynomial, correct? So 7 is a polynomial. And there is nothing special about 7. It's just a constant. So instead of thinking about 7 by just the case 7, you can think about any constant you want. Let's call it c. Any constant you want, you can say that this is a polynomial for the same reason, because again, you can take it times x to power 0, and this is a finite sum of which is a sum of one entity, and the coefficient here is a constant, that guy is a constant, and x to power 0, so 0 is an integer greater than or equal to 0, correct? So a constant, any constant, is a polynomial, and hence you can think about polynomials as generalization of generalization of numbers. Okay, so this is the point I wanted to make here. All right, so this is technically those two lines. So all the AIs, all these guys, a n, a sub n minus 1, and so on, they're all real numbers, and the power n, that guy, the highest one, is a non-negative integer, and a sub n is not 0. So that number a sub n is supposed not to be 0 for us to say that the polynomial function is of degree n. Okay. All right. So to summarize again, what's a polynomial function? It's a finite sum of terms that look like constant times x to some power, and that power is should be an integer greater than or equal to 0. The highest power that occurs in the sum is called the degree of the polynomial. For example, the degree here was 1, the degree here was 2. Okay? All right. So these numbers, the highlighted ones in orange, they are called coefficients of the polynomial. These are the multiplicative constants, right? So an is the constant that you are multiplying xn with. So that guy is called the coefficient of the xn term. This is called the coefficient of the xn minus 1 term, and so on. A sub 1 is called the coefficient of the x term, and a sub 0 is called the coefficient of x to power 0. This is also called the constant part, the constant term, because x to power 0 is 1, right? So you're left with just a constant for the last expression here. Okay, so the number a0 is either called constant coefficient or constant term, as I said. All right, and the number a sub n, who's a sub n? It's the coefficient of the xn term, that guy. So what's the name of this guy? It's called the leading coefficient. It's the leading coefficient because it's leading in the sense that it has the highest, it's the coefficient of the highest degree term, right? The term which has the highest power. Okay, so that coefficient is called the leading coefficient, and the term anxn, that term, the coefficient together with x to the highest power, is called the leading term. So the leading term is the term which has the highest power. Okay, let's take a few examples. Here are some examples of polynomials. Even though we discussed a few, let's talk about the first one. P of x is equal to 3x5 plus 6x4 minus etc. So does this one look like a finite sum? Yeah, I have bunch of sums, right? 1, 2, 3, 4, 5, 6 terms here I have. So it's a sum of 6 expressions, 6 entities. You're gonna say, oh, I have a minus. Sure, but the minus can be thought of as addition or adding the opposite, right? Adding the opposite. Similarly here, adding the opposite. And likewise, adding the opposite, right? So now you clearly see that it's a finite sum. And in this case, how many summands? 1, 2, 3, 4, 5, 6, as we said. So I have 6 summands. Certainly it's finite sum. And each of these looks like a constant times x to a power where this power is an integer greater than or equal to 0. Correct? Let's talk about the first one, this term here. Who's the constant? It's 3. So it's certainly a real number, so 3. And then who's the exponent? Who's sitting here? It's the 5. It's the 5. Is the 5 an integer greater than or equal to 0? Yeah. So this first term is okay, right? It looks like that. That's what I mean by okay. Next, for the second term, this term, does it look like a constant times x to an integer greater than or equal to 0? Yeah. 6 is a pure constant. And the dot here, the exponent is 4, right? Which is clearly an integer greater than or equal to 0. So this term is okay as well. How about the third term? How about this term? So this is also of the form constant times x to an integer which is greater than or equal to 0, in this case 3. Correct? And so on and so forth. For example, here the constant is simply 1, right? It's simply 1. That's the constant. And the power is 2. For this term, for this one, the constant is -7 and the power is 1, right? The power is 1. And for the last term, the constant is -pi. This is a constant. I mean, it's a number no matter how... I mean, it's an irrational number, I know, but it's a number at the end of the day. So it's a constant times x to power 0, right? Times x to power 0 in this case. And certainly 0 is an integer greater than or equal to 0. Okay? So each of these summand is actually of this form, and as such, the sum of all of this, which is called p of x, is a polynomial. What's the degree of this polynomial? What's the highest power that sits on the exponent part? It's the 5, right? So this p of x is a polynomial of degree 5. Okay? All right. So similarly for the other ones, for q of x, this is going to be the same thing. Probably one comment is the 8/3. This is still a constant. I didn't say that this coefficient has to be an integer. It can be any constant like pi or whatever, right? Square root of 2. All these numbers are, as long as it's a number, it can sit as a coefficient, and so on and so forth, right? How about now if I change the following? If I take the following situation. What if I have, instead of this, I have 4x squared minus 1? Is this a polynomial? Is this a polynomial? Yeah, this is a finite sum again. 2 summands, 1, 2, each of which looks like a constant times x to some power where this power is an integer greater than or equal to 0. And this guy, in this term, 4 is the constant, 2 is the power, and this term, the constant is -1 and the power is 0 for this term, right? So certainly this is a polynomial of degree 2 in this case. You're gonna tell me, oh, what happened to the x term, right? It looks like there is no x, like here, I had an x term. Well, the x term disappears, which means that its coefficient is 0, right? So the x term disappeared, and the only way it can disappear is when the coefficient is 0. Correct? So So in this case, this would be like a sub 2 in the definition. This would be a sub 1. A sub 1 is 0. And negative 1 would be the a sub 0 guy. Correct? Okay. But this is still of degree 2. Okay. All right. And in the third one, n of x, this is of degree 1. We discussed this before. And m of x, this is a constant, which means of degree 0, right? Because you can think about 9, as we said before, as x to power 0. So this is a polynomial of degree 0. Okay? So numbers or polynomials are generalization of numbers because numbers are particular cases of polynomials. And because of that, because numbers are special cases of polynomials, we used to divide, for example, numbers, right? So we used to divide numbers, like we used to do 9, let's say, divided by 2, correct? So we get 4 and the remainder is 1. 9 was called dividend, correct? And the 2 was called divisor. The 4 was referred to in this case as the quotient, and the 1 is the remainder. And what was true about the remainder? The remainder is always smaller than the divisor, correct? So we're gonna try to carry this out to the level of polynomials because, as we said, numbers are special cases of polynomials, and we used to divide. We're gonna try to actually divide polynomials as opposed to numbers. So we're gonna carry this this ability to that level, to the level of polynomials. And the next theorem actually tells us that this is possible. Let's read that, the division algorithm. If p of x, which is gonna play the role of the dividend in this case, so if p of x, which is the dividend, and d of x, that's gonna be the divisor, are polynomials with d of x not 0, so the divisor cannot be 0, right? Then there exist unique polynomials, q of x, which is going to be the quotient, and r of x, which is the remainder. So this is the remainder. But now we don't have numbers. They are generalized numbers, which are polynomials. So where the degree of the remainder is smaller than the degree of the divisor. So in this case, r is the remainder. The degree of r, this is a polynomial, so I can talk about its degree, right? Like in the definition. So r of x, the degree of r of x, the remainder, is smaller than the degree of the divisor. Such that this happens, which means the dividend is equal to the divisor times the quotient plus the remainder, right? So like we used to do. So if this is p of x, which is the dividend, d of x is the divisor, q of x is the quotient, and r of x is the remainder. The remainder, based on this division algorithm, based on this theorem, should be smaller than the degree of the divisor. And as such, we can write p of x equals to q of x times d of x, this product, plus the remainder, right? This is what this is saying. Okay? So that algorithm, that division algorithm, or that theorem, guarantees that what we used to do for numbers, right? What we used to do for numbers at the level of division can actually be carried out to the level, to the more generalized level, which is the level of polynomials. Okay? Let's now go to the book and see the division algorithm in action, how it can be used. That's 2.3, page 279. And let's do number 10. So use long division, which is the division algorithm, to divide those two polynomials. Okay? So let me copy that. So let's take it here. I need to divide this guy, 2x cubed minus 7x squared minus 65, by x minus 5. So how does it go? By the division algorithm we just discussed, I can do so, right? And how can I do it? This is the algorithm, this is the process. So I have the dividend, which is 2x cubed minus 7x squared minus 65. You always write it, I mean, to do this algorithm, to do this process, you always write the polynomial in a descending fashion for exponent. So the highest term, right, the highest degree term, followed by the next highest, and so on. So the degree 3 is higher than the degree 2, which is higher than the degree 0, right? This is of degree 0, but we don't write this guy. And we're going to divide by x minus 5. Also, I'm going to write this as in a descending fashion for exponents. So x is degree 1 and 5 is of degree 0, right? Okay. So by the division algorithm, p of x is 2x cubed minus 7x squared minus 65. D of x, which is the divisor, is x minus 5. And q of x is the guy that's going to be found here. And r of x is the remainder, right? And what do we know about the remainder? What do we know about the remainder? The remainder is of degree less than the degree of the divisor. Who's the divisor here? The divisor is x minus 5, right? So what's the degree smaller than the degree of x minus 5? This is of degree what? This is of degree 1, right? This is of degree 1, correct? And what's the degree smaller than 1? Based on the division algorithm, r of x has to be of degree smaller than 1, right? And what's that? The degree has to be always greater than or equal to 0, and in this case it has to be smaller than 1. So what's that guy then? It has to be a constant. A constant, because that's the only polynomial whose degree is 0, which is smaller than 1. One more time. If you divide this by x minus 5 based on the algorithm that we just discussed, the theorem above, we know that the remainder is going to have degree smaller than the degree of the divisor, right? Who's the degree of the divisor? What's the degree of the divisor? This is the divisor. It's of degree 1. So the remainder has to have a degree smaller than 1. And since the degree is always 0 or more, so the only option I have is that smaller than 1 is 0, right? So the degree of the remainder has to be 0. And what are those guys whose degree is 0? They are constants, correct? They are those guys, right? Times x to power 0. So they are constants. So I know for sure the remainder is going to be a constant. The question is we need to find that constant. Okay? All right. So now I have some idea about how the remainder is going to look like. Very good. So let's go through the division. How does it go? So you're gonna focus on the leading term in the existing polynomial, which is 2x cubed. And you're gonna ask yourself, what should you multiply this guy with to get 2x cubed? So how about the numerical part? What should you multiply? There's a 1 here as a coefficient for x. What should you multiply 1 with to get it 2? Well, clearly you have to multiply by 2, right? Let's make it bigger. Moving on, how about the x guy? What should you multiply x with to get x cubed? Well, that guy should be x squared, right? Because you add the powers. If you are multiplying x with x squared, multiplying two exponential expressions with the same base, you keep the base and you add the powers. 1 plus 2 is 3, right? So x squared times x is going to give you 2x cubed. Now check the whole term, the whole purple term. 2x squared times x, if you multiply this guy with this, you're going to get 2x cubed, right? Okay. And now 2x squared, so for sure if you multiply this with this, you're going to get 2x cubed. Let's do it. That times that is going to be 2x cubed. And that times the negative 5 is going to be negative 10x squared, right? Negative 10x squared. Okay. And what did we use to do at the level of numbers? We used to subtract. We used to subtract the guy here from that guy here, right? So we used to perform the subtraction. Okay. So technically what I'm doing here vertically in a vertical direction or vertical fashion, I'm doing the following horizontal operation. I'm taking the blue part, the blue polynomial, and I'm subtracting from that I'm subtracting from that. So I'm subtracting from that purple guy, right? That purple guy. Okay, am I correct? This is what's happening. This is what's happening. This is what's happening here in vertical fashion. But the whole package here and the whole package here, right? From the entire blue guy, I'm subtracting the entire purple guy. So I get this. And let's do it in a horizontal fashion. So what do you do next? You drop the parentheses, right? And you let the minus kick in. And by kicking in, I mean everybody inside is going to switch sign. So you get 2x cubed minus 7x squared minus 65. That's the blue guy. Minus, now this minus is going to kick in. Minus 2x cubed plus 10x squared, right? So the minus kicked in. And that everybody is going to switch signs. So the 2 is going to become negative 2. And the minus 10 is going to become plus 10. Correct? So you get this. And now if you combine like terms, what do you get? This guy and this guy cancel each other. This guy here and this guy here, we get what? 10x squared minus 7x squared is 3x squared. And minus 65. Correct? So if you subtract the purple from the blue, you get 3x squared minus 65. So that's exactly what's going to be done here. Whatever I did here, it's going to be done in a vertical fashion. I'm not going to always write it in a horizontal fashion. I'm going to do it vertically. So let's build this this momentum. So keep in mind, that's the model that you have, but vertically. So 2x cubed minus 2x cubed. This is what happened here, right? That's 0x cubed, so no more x cubed. And then the negative 7x squared minus the minus, that becomes a plus 10, and plus 10x squared minus 7, it's the 3x squared, right? It's the 3x squared, correct? And then the minus 65 doesn't have a company here. This purple guy doesn't have a constant term, so I'm gonna just carry that minus 65. Okay, so that's what's going on in this vertical fashion, in this vertical writing. Okay, so but this is the essence. This is what's going on. Okay, so I'm gonna erase this for the sake of space, and let's keep rolling. So what used to be of degree 3, now the degree 3 became degree 2. So we dropped one power, and now I'm gonna do the same game between this guy and this guy. So what I've done between this guy and x minus 5, now I'm gonna do it between this guy and x minus 5. Okay, so what did I do at the time? I asked myself, what should I multiply x with to get 3x squared? So what should I multiply x with to get 3x squared? For the numerical part, it should be 3, right? Plus 3. And for the x term, for the x guy, it has to be x, because 3x times x is 3x squared, right? So you get this. 3x times x is 3x squared. And now 3x is going to also talk to the negative 5. 3x times the negative 5, that's negative 15x, correct? And then the same thing, we're going to subtract the pink from the green. Okay? All right. And what do we obtain? If you subtract 3x squared, the pink one, from the green 3x squared, you get 0x squared, so no more x squared. And then what would be the next exponent after, the next exponent smaller than 2? It's 1, right? It's that guy. I don't have an x term upstairs, so how about this guy? This is gonna be, so it's technically 0x upstairs. I don't have an x term, so which means 0x, minus the minus, so this is a plus 15x, right? And the constant is gonna be, I don't have a constant here, so it's gonna be by itself, minus 65. So if you do it again, if you do it horizontally, I'll do it one more time. If you do it horizontally, so the green part, which was 3x squared minus 65, I'm gonna subtract from this the pink guy, which is 3x squared minus 15x. I'm showing to you what I've done vertically, just to build that intuition into doing things vertically after that. Okay, so what did we get? Or what do we get here? That's 3x squared. I'm going to destroy the parentheses. Minus 65 minus kicks in, minus 3x squared minus the minus is plus 15x, right? That's exactly what I've done here. Those guys cancel. 15x minus 65. So you see this result and this result are the same. I'm showing it to you horizontally just to build some momentum and some intuition on how to do it vertically. But again, what's going on here is exactly what's going on here, but we do it this way because we used to divide in this fashion, right? So we used to do it that way at the level of numbers. Very good. Let's erase this. And now we're gonna keep rolling, right? We're gonna keep doing what we've been doing, but now between this guy and this guy. Correct? Remember, the remainder is guaranteed to be a constant, so I'm not gonna stop until I get a constant here. This is not a constant, right? This is a polynomial of degree 1. So this is still a polynomial which is not less than the degree of that 1, right? This is of degree 1 and this is of degree 1. Certainly 1 is not smaller than 1. Based on the division algorithm, you stop when the remainder becomes of degree smaller than the degree of the divisor. And I haven't reached that stage yet. Okay, so one more. Same game. 15x, I want to get to 15x by multiplying x by something. What should I multiply x by to get 15x? 15, right? 15 times x is 15x. Correct? So I get that. And then 15 now is going to talk to the negative 5, right? 15 now is going to talk to the negative 5. So what's 15 times 5? What is it? 75, right? So minus 75. And then what do? We subtract. We subtract the green from the orange, right? Okay, so let's do that. And what do we obtain? 15x minus 15x, 0. I mean, remember, we should get the 0 because that's how we engineered that guy, right? So that it cancels that term. And minus 65 minus the minus is plus 75. Minus 65 plus 75, that's a 10, correct? And that's the constant I was looking for. That's the remainder. That's the remainder. Correct? So that's the remainder that the division algorithm promised me to get. R of x, which is of degree smaller than the degree of the divisor. The divisor here is of degree 1. So I knew I'm going to get to a constant at the end as discussed before. Okay? So we stop, the division algorithm stops, and then what do we obtain? So what do we obtain at this point? The dividend is equal to the divisor times the quotient plus the remainder. This is what the theorem tells us, right? So the polynomial, the dividend, p, is equal to the divisor times the quotient plus the remainder. All right. So this means what? This means 2x cubed minus 7x squared. This is the dividend minus 65. Minus 65 is equal to the quotient x minus 5. Sorry, the divisor times the quotient, which is 2x squared plus 3x plus 15 plus the remainder, and the remainder is 10. Agree? Let me just grab this and put it here just to have more room. Okay, makes sense? So this is what I get. P of x, the dividend, is equal to divisor times the quotient plus the remainder. Okay? And what did they tell us? They told us to divide this guy by x minus 5. So technically what they want is they want a writing for this guy, 2x cubed minus 7x squared minus 65 divided by x minus 5. So they want this quotient to be written and see what happens. Okay? So how do I get to this quotient? Well, I have this guy, which is this guy, correct? And how do I get to this quotient? I just have to divide I just have to divide this purple guy by x minus 5. Okay? So I'm going to divide this guy by x minus 5, which means I'm going to divide both sides by x minus 5 because this guy here is the same as the other side. Correct? So to get to that, to get to what they want, I'm going to divide both sides. So I'm going to divide both sides by x minus 5. Okay? So which means this side and this side by x minus 5. We divide by the same thing. I'm going to copy everything that's upstairs, right? So I'm going to copy this part. So I get, it sits here, and I'm going to copy this part, and it should sit over here. Correct? So I get that. Okay. And now, can we simplify this side? Can we simplify this side? Well, this is the same denominator, right? X minus 5 is the same denominator. Let me ask the following question. Let me ask you the following question. If you have a plus b divided by c, isn't that the same as a over c plus b over c? Isn't that thing the same as this? Probably you used to do it backwards. So you have the same denominator, which is c in this case. If you want to go back, you can glue the same, they have a common ground. You can glue them together and you get upstairs a plus b, and that common ground becomes the common denominator for that sum, a plus b. Correct? So you can decompose it backwards. So if you have such a thing, you can decompose it like that. And this is what I'm going to do. I'm going to think about all this block as the a over here, this block as the b, and this block as the c. Okay? So this is indeed of the form, structure-wise, it looks like a plus b over c, right? I'm going to use that writing for it. And what do I get? Let's take it to this page. What do I get? So I get a over c, so that's a, so x minus 5, so x minus 5 times 2x squared plus 3x plus 15 divided by x minus 5. That's the a over c guy, right? That's the a over c, plus the b over c, and the b is 10, right? So 10 over x minus 5. So we get that. So we get that. Okay? All right. And what's the benefit of doing it this way? Now look, the x minus 5 upstairs and the x minus 5 downstairs, that's a common factor which can be simplified. Correct? Just for this, for the first fraction. Right? So we get what? We get, so we're left with a denominator 1 if we simplify. So we're getting 2x squared plus 3x plus 15. That's the whole thing here because those canceled. Plus this fraction, 10 over x minus 5. Okay? So this would be the answer. This would be the answer to what they wanted. What did they want? They wanted this guy, right? And what is that? It's right there. It's right there. And at the end of the day, we managed to write it as follows, as here, right? So at the end of the day, we got that this guy here is equal to what they want. Make sense? So we get that. And this answers the question. So what's the process again? We run the algorithm, the division algorithm, by first writing the polynomial. We always write in descending fashion for exponent, as we said, for both for the dividend and for the divisor. And we start asking ourselves, what should you multiply the first term in the divisor to get the first term in the dividend, and so on and so forth. We keep playing it over and over until I get to a stage where the remainder is going to be of degree smaller than the degree of the divisor, right? By the division algorithm. And at the end, we write that. So we write that, so which means the dividend is equal to the divisor times the quotient plus the remainder. And then we answer the question. The question is they want this guy to be over x minus 5. So I divide both sides by x minus 5 and try to simplify here. and get to that stage. So this guy, this fraction is actually this piece. Okay? All right, so let's do another example. This is still on page 279. Let's now do number 12. Okay? All right. So we need to divide this polynomial by x plus 3. So this polynomial here is of degree 4, right? It's just written, the exponents are increasing as opposed to what we used to, decreasing, right? And in order to do the long division, we're gonna write the dividend and the divisor in a fashion where the exponents are descending. Okay, so what I'm gonna do is I'm gonna copy it as such. So this is the dividend. I'm gonna start with the highest one, so 3x4 plus 17x cubed plus 20x squared minus 28x minus 48. All right, minus 48. Let's do it here. Minus 48. Okay, and I want to divide this by x plus 3. So this is already in a descending fashion for exponents, so I'm going to keep it. All right, and then I want to multiply x. So the same algorithm, right? So I'm going to multiply x by something to get the leading term here, which is 3x4. That's clearly 3x cubed, right? 3 times 1 is 3, and x cubed times x is, you add the powers, 1 plus 3 is 4, right? So you get 3x4, and 3x cubed times the 3, it's plus 9x cubed, right? And then, as we used to do, we're going to subtract the purple from the green, right? And what do we obtain? What do we obtain here? So 3x4 minus 3x4 is 0. 17x cubed minus 9x cubed is 8x cubed, right? And 20x squared, I don't have x squared here, right? So that's going to be itself. And I don't have an x, so it's going to be itself, minus 28x and minus 48. Because again, I don't have a constant part to talk to that, right? So I get this. All right. So the degree 4 now came down by 1. So I have 3 now. And the same game. This is already arranged in a fashion where the exponents are descending. Now I'm gonna ask myself, what should I multiply x with to get 8x cubed? And that's clearly 8x squared, right? So 8x squared. And if you multiply ax squared by x, you get that 8x cubed. And if you multiply 8x squared with the 3, you're gonna get 24x squared. And that's it, right? So I don't have any more terms. So I'm gonna subtract the guy downstairs from the guy upstairs. And what do we get? 8x cubed minus 8x cubed, 0x cubed. 20x squared minus 24x squared. That's minus 4x squared. And I don't have an x term here. I don't have a constant, so they're going to be themselves. Remember, this vertical writing is the same as the horizontal one. So if you're not comfortable with this and you still haven't built intuition, go for the horizontal one and subtract that guy, right, from that guy. Okay. And this is what you should get. Very good. So now from 3 down, exponent 3 down to 2. So I want to ask myself, what should I multiply x with to get negative 4x squared? And this is negative 4x, right? Negative 4x times negative 4x. Negative 4x times x is negative 4x squared. Okay. And negative 4x times the 3 is going to be negative 12x. All right. And let's subtract. And what do we get? Negative 4x squared minus itself, that's 0x squared. Negative 28x minus the minus is going to be plus 12x, right? So negative 28x plus 12x, that's negative 16x, right? Negative 16x minus 48. Okay? Should I stop here? Are we done? No, because the degree here is still 1, right? This is of degree 1. And the degree of the divisor is 1. So we can keep going. When do we stop? We stop when we drop below the degree of the divisor. What's the degree of the divisor? Degree 1. What's the degree of the remainder? What are the options for the degree of the remainder? The only option is that's smaller than 1. It should be 0, right? Because the degree is non-negative. So the only option smaller than 1 is 0. So I should get at the end the remainder for sure. For sure the remainder is going to be of degree 0, a polynomial of degree 0. And what's a polynomial of degree 0? It's a constant, right? It should be a constant. That's for sure the format of the remainder. Okay? All right. So let's do it one more step. As you realize, degree 4 down to 3, down to 2, down to 1. And then one more step is going to put me of degree 0, which means it's going to put me at the constant level, right? Let's do it. So same thing. What should I multiply negative 16? Sorry, what should I multiply x with to get negative 16x? Well, that's negative 16, right? Negative 16. Negative 16 times x is negative 16x. And negative 16 times 3 is negative 48, right? Is negative 48. And I'm going to subtract the bottom from the top, but you realize that what I'm going to get is I'm going to get 0, right? That I'm going to get 0. That's not what's expected. What's expected is a constant at the end. But any constant is of degree 0. It just happens here that the number is 0 as well, right? 0 is a constant, and at the same time, it's the number 0. So I wasn't expecting the number 0. What I was expecting a constant, right? Which is of degree 0. Degree 0, not number 0. Okay? All right, so that's a nice remainder. It's just 0. Very good. So now we're going to write this divided by that, as we did above. So let's do this. So I'm going to get this guy divided. So this guy divided by the x plus 3, right? So let's do it. So divided by x plus 3. And what did we get? Okay, you know what? Let's do it one more time. Let's write the whole thing. So I have this is equal to, that's equal to, this is the dividend, is equal to the quotient times the divisor. So x plus 3 times the quotient, which is this. This is the quotient. So 3x cubed plus 8x squared minus 4x minus 16. This is the quotient times the divisor plus the remainder, right? How much is the remainder? 0. So technically I should put plus 0, but plus 0 is that entity, right? Okay. All right. So that's what they want. They want this divided by x plus 3, so I need to divide both sides by x plus 3 here. I need to divide both sides by x plus 3, right? I need to divide this guy by x plus 3 and this guy by x plus 3. Let's do that. So let's copy it. And we get this. All right. So divided by x plus 3. And here divided by x plus 3. Okay. All right. This is what they want. Now I want to simplify if possible here. Let's simplify this. I clearly have a common factor, the x plus 3 guy, right? That's a common factor. And what do I obtain? Simply the quotient. Simply the quotient. So just 3x cubed plus 8x squared minus 4x minus 16. Okay? So long story short, this polynomial divided by x plus 3 is simply this guy, because the remainder was 0. All right, let's do another one. Let's do now number 18. Same question. So number 18. So I need to divide now this 4th degree polynomial, it's a 4th degree, I want to divide it by a 2nd degree polynomial, right? So I have 12x4 minus 4x cubed plus 13x squared plus 2x plus 1. That's playing the role of the dividend divided by the divisor, which is 3x squared minus x plus 4. Okay? Alright. Same thing. This is already arranged in a decreasing fashion for exponents. Similarly here, it's good to go. Let's do it. So I want to multiply 3x squared by something to get 12x to power 4. For the numerical part, I need to multiply by 4, right? I need to multiply by 4. So that's the numerical part. And for the x guy, x squared times what is x to power 4? That x squared, right? Because you add the powers. It just happens that 2 times 2 also is 4. But in this case, I'm adding the power. X squared times x squared is x to power 4. Okay? Alright. And now this guy is going to, as usual, be multiplied by everybody here, right? By everybody. So if it multiplies itself with 4x squared, we get 12x4, which is anticipated because I need the same guy. Now this guy talking to negative x, it's going to be negative 4x cubed, right? Negative 4x cubed. It's unfolding nicely here. 4x squared times 4 is 16x squared, right? So plus 16x squared. All right. And then I'm going to subtract the orange from the purple. And I obtain what? This minus itself is 0. That guy minus 4x cubed minus itself. So that's also 0. 13x squared minus 16x squared. That's negative 3x squared. And then I don't have a company for 2x, so I'm going to just copy the 2x and the 1. Okay. All right. This is arranged in a descending fashion for exponents, so I'm going to keep running the same program. And what do I get? What do I need? I need to multiply 3x squared by something to obtain negative 3x squared. It's simply multiplied by negative 1 then, right? Multiplied by negative 1. And again, negative 1 is going to talk to everybody, to all this polynomial. Negative 1 times 3x squared, negative 1 times negative x, and negative 1 times the 4. What do we obtain when negative 1 talks to 3x squared? We get negative 3x squared. Negative 1 times the negative x is plus x. And the negative 1 times the 4 is negative 4, right? Is negative 4. Okay? And then subtract the brown one from the blue. And we obtain what? We obtain what? This and this cancel. 2x minus x, right? 2x minus the plus, so minus x is minus 1x. So 2x minus x is x. Plus 1 minus the minus is plus, right? The opposite of the opposite is plus. So 1 plus 4 is 5. Correct? So we get x plus 5 so far. And do we stop here? What's the degree of this guy? Degree 1, right? Degree 1. What's the degree of this guy? Degree 2. So is 1 smaller than 2? Yes. So the degree, so because of that, that's going to be the remainder, right? So we stop whenever we drop below the degree of the divisor. Okay. And now let's rewrite the whole thing. So this guy, which is 12x4 minus 4x cubed plus 13x squared plus 2x plus 1, that's the dividend, is equal to the divisor, which is 3x squared minus x plus 4, the divisor, times the quotient, which is 4x squared minus 1, right, plus plus the remainder, which is x plus 5. Okay? Alright. What do they want? They want this divided by that, right? This is what they want. They want a writing of this fraction. Okay, so it suffices then to divide both sides by 3x squared minus x plus 4 to get to what they want. Let's copy it. Oops. One more time. So let's copy this part. Okay. And as I said, I want to divide both sides by this divisor. So divide this side by 3x squared minus x plus 4, and divide this side as well by 3x squared minus x plus 4. Okay? Alright, let's move this equality to this level. Alright, very good. Okay, so now I want to play the same game as before. What game? What game I'm talking about? This game here. This one, right? So a plus b divided by c is a over c plus b over c. So that's what I'm gonna do. That's gonna be equal to, I'm gonna treat this piece as a, and I'm gonna treat this piece as b, right? And this one is gonna be the c. Correct? So that yellow guy is gonna be the a, the blue one, the blue highlighted one, is gonna be the b, and that guy is gonna be the c downstairs. And then what is that? Let's revisit this concept. So a plus b over c is equal to a over c plus b over c. That's what we said. Okay? Alright, and what do we obtain? So a over c, this over c, so 3x squared minus x plus 4 times 4x squared minus 1 divided by the c, which is 3x squared minus x plus 4, right? Plus the b over c, so this b over c, plus x plus 5 divided by 3x squared minus x plus 4. Okay? And as you may guess, I'm setting the stage for the simplification to take place. That's the same factor, and we obtain 4x squared minus 1, right? This whole thing becomes this, plus this quotient. So x plus 5 divided by 3 x squared minus x plus 4. Alright. Okay, so what they wanted, which is this, happens to be all of this, right? So this would be the answer. Alright. Let's now make the following observation. Okay? Let's make the following observation. Let me take you back to number 10 and ask you the following question. Let me ask you, what is, let's call this guy P of x. Okay? Let's call this guy P of x. And let me ask you to find, so this is like an addendum, right? So find P of 5. Okay? So find P of 5. So P of x is this much. I want to evaluate P at 5. So instead of x, the input is going to be 5, right? So P of 5 is going to be 2 times 5 cubed minus 7 times 5 squared minus 65. Correct? Alright. So 5 cubed is 125, and 125 times 2 is 250. 5 squared is 25, and 25 times 7 is 175 minus 65. And how much is this? Minus 175 minus 65 is 240 minus 240. 250 minus 240 is 10, right? It's 10, which is what? Which is the remainder. Interesting. So if you evaluate P at 5, it happened to be the remainder. Alright. Is this a coincidence? Well, let's try it for the other one. How about this? How about we call again this guy p of x? Let me change the color here. So how about I call this entity p of x, which is the dividend, right? And let's divide by, or let's find p of negative 3. I'm gonna find p of negative 3. Technically, I'm thinking about x plus 3 as x minus the minus 3. So I'm evaluating p at this guy that comes after the minus, like I did before. Why? You're gonna see why. This is the observation I'm making. Like I did before, I evaluated p at 5, provided there is a minus in front, right? So it happens that this guy that comes after the minus is 5, whereas here the guy that comes after the minus happens to be minus 3 in this case, right? It's the minus 3 because we have x plus 3. Alright, so p of negative 3. So I want to evaluate p at negative 3, which means I'm gonna, instead of x, I'm gonna have minus 3 all the way, right? So that's gonna be 3 times minus 3 to power 4 plus 17 times minus 3 to power 3 plus 20 times minus 3 squared minus 28 times minus 3 minus 48. Okay? All right. Let's evaluate this. What's minus 3 to power 4? Well, minus 3 to power 4 is certainly positive because I'm raising it to power even. And 3 to power 4 is like 9 squared, right? So this is AD1, and AD1 times 3 is 243. Next, how about this? Minus 3 cubed. Minus 3 cubed is a negative entity. And what's 3 cubed? Well, 3 times 3 is 9, 9 times 3 is 27, and 27 times 17 is 459. And over here, what do I have? Negative 3 squared is 9. 9 times 20 is 180. Minus 28 times minus 3, that's a plus. And 28 times 3 is 84. And minus 48. And let's do that. 243 minus 459, that's minus 216, plus 180, that's minus 36, plus 84, that's 48, and minus 48 is 0, right? Agree with that? So what happens then? P of negative 3 is 0, which also coincides with the remainder. All right. So it looks like it's not a coincidence. It happened 2 times in a row. So it's worth actually exploring that. And what is the thing that I need to explore? If I'm dividing a polynomial, like I did here, with x minus a guy, the guy here happens to be minus 3, over here in the previous one it happened to be 5. So if I'm dividing, that's the claim I'm gonna make. If I'm dividing a polynomial by x minus a number, right, in both cases, the remainder, I'm gonna claim that it's p, the polynomial evaluated at this number, right, like I did here. The remainder happens to be p evaluated at this number. That's the claim. We strongly believe it's not a coincidence. It happened a couple of times in a row. So it's worth actually exploring that and to see why this is not a coincidence. Let's consider that. So let's write the conjecture. Let's call it conjecture. So conjecture. The remainder of or when dividing a polynomial poly for polynomial, a polynomial p of x. So when dividing a polynomial p of x by x minus a number, right, whatever this number is, how about we call it c, constant c, where c is a constant, where c is a real number. So the remainder when dividing is p of that c, right? So let me be very clear. Whatever this guy is, let's call it the pink c, is gonna be that guy here, right? It's gonna be this guy here, p of c. This is what this is the observation we made, right? We divided p of x by x minus a number. The remainder happened to be p of c. Why this? I mean, this is useful. If it's correct, it would be useful because instead of having, if you are only interested in the remainder, so if you are only interested in the remainder, then you don't have to go through the long division to wait to get to the remainder. If what we said is correct, simply evaluate p at that number c, right? In this case, c happened to be 5, and the other case happened to be -3. Correct? So it would be calculation efficient in some sense, right? To actually just, instead of going through the entire process of long division to wait to get to that remainder, we can only evaluate the dividend at that number c. Okay? All right, so let's see if this conjecture is correct. All right, why this conjecture is correct? Well, by the algorithm division, or division algorithm, so by the algorithm, which is the division algorithm, what did we know? So what am I saying here? What do I mean by division algorithm? It's the algorithm that we talked about before, right? Namely this one, the next page, this one, that one. So if you are dividing p of x by d of x is the divisor, so in our case is x minus c, then you're gonna get a quotient, a unique quotient and a unique remainder, so that the remainder is of degree smaller, right? The remainder is of degree smaller than the divisor, the degree of the divisor, such that this writing holds, right? So the dividend is equal to the quotient times the divisor plus the remainder. So this is the division algorithm I was talking about. So let's keep going. So by the division algorithm, we know that there exist unique q of x, right? Unique q of x and r of x, so r of x, which is the remainder, such that the degree of r of x is smaller or less than the degree of the divisor. The degree of the divisor. And who's the divisor here? Who's the divisor? What am I dividing with? I'm dividing this guy by this guy. So that's the divisor. That's the divisor. So the degree of r of x is going to be less than the degree of x minus c, the polynomial x minus c, the divisor. Correct? This is what the division algorithm tells me. Such that p of x, the dividend, is equal to the quotient times the divisor, which is x minus c, plus the remainder. Am I correct? This is what the division algorithm tells us, this thing here. Now I have a special guy, this guy, which is the divisor. All right, let's pay attention to the following sentence here. The degree of r of x is less than the degree of x minus c. So what's the degree of x minus c? C is a constant, like 5, 6, whatever. What's the degree of x minus c? This is 1, right? The degree of x minus c is 1. So this is 1 here. Agree with that? So the degree of r of x must be smaller than 1. So what are you left with then? if the degree of r of x should be at the same time greater than or equal to 0 and less than 1, and it's an integer, right? The degree is always an integer. So you're left with just the degree being 0 then. Correct? The degree has to be 0 of the polynomial r of x. So let's record this. So since the degree of r of x, I'm gonna use DEG for degree of r of x, is smaller than the degree of the divisor, x minus c. How much is this? This is 1, right? This is of degree 1. It's right there. This is of degree 1. At the same time, this degree cannot drop below 0, right? So at the same time, this is bigger than or equal to 0 and integer. So what are you left with? Then r of x, the degree of r of x must be 0. Must be 0. Must be 0. Correct? That is to say, what are those polynomials? Because r of x is a polynomial. So what are those polynomials which have degree 0? That is, r of x is simply a constant. Is a constant. Correct? So it's a constant. How about we give it a name? How about we give this guy a name? So say r of x is a constant. I know it's a constant. Let's give this constant a name. What's your favorite letter for constant? Let's say k. Okay. So what's k? I know that r of x is of degree 0, so it has to be a constant. I'm calling it k. Okay? I'm calling that number k. So this is a pure constant, right? It's a pure constant. All right. So this guy then, I can take it out and replace it by the k I was talking about, right? So let's write that. So thus, p of x is equal to q of x times x minus c plus the k. Plus the k, right? From this. All right. And now let's pay attention to this equation. This equation should hold for all x, right? This is an identity. This should hold for all x. This should hold, which holds for all x and r, right? For all x and r. So this identity here that we have holds for all choices of x, no matter what you replace x with, right? No matter what you replace x with. You put it here, you put it here, you put it here, you get a true statement. The left side and the right side should be the same. Correct? So how about replacing a special x? Let's make a choice of a special x so that what we want, we find k. You have to understand here, the conjecture is the remainder is this guy, right? And who's the remainder so far? The remainder so far is k, correct? The remainder is k. So what do I need to show? I need to show that k is actually p of c, right? P of c. All right, so let's do it. So since this holds for all choices of x, how about we make a special choice? So, and let's take x to be c. Okay. So hence, if we choose x to be c, x equals c, the equation, let's call equation star, must hold, right? Must hold. Because it holds for all choices of x. No matter what x you choose, this holds, star holds. So in particular, if you choose that number c, you're going to get a true statement. And what do we get? As such, we get, let's read it together. P of c, I'm replacing x by c. P of c is equal to q of c, right? Times c minus c plus k. And what's c minus c? 0, right? So that guy is 0. And 0 times any polynomial is 0. So now this whole thing is 0. And what do you obtain? You obtain that P of C is equal to K. So that is to say, P of C is equal to K. As conjectured, right? As conjectured. This was the conjecture, right? The conjecture was that the remainder, which is K, is equal to P of C. So the conjecture then holds. This is a theorem now, because we just showed it. Okay? So we observed this by the previous two examples, and then we conjecture it, and then we proved it because we felt like this is the case. Why don't we conjecture and prove that? We did that, and this is actually a theorem, and it's called the Remainder Theorem. And here's the statement. Here's the statement. If the polynomial p of x is divided by x minus c, where c is a pure constant, then the remainder is the value p of c, right? So let me take you back to that example where we started observing that. And this example, number 10, we divided by x minus c. That's the c, right? We divide p of x by x minus c. The c was 5, which means if you want to find the remainder, if you are only interested in the remainder, not in the quotient, if you're only interested in the remainder, that guy, simply evaluate p at that number c. And this indeed matches goes along with the proof, with the theorem that we just discussed. And the next one too. And number 12. So c happened to be here, right? Which is 3 in this case. X minus the minus 3 happens to be c, so I'm gonna evaluate p at minus 3 to get the remainder. So if you are only interested in the remainder, then evaluate p at that number c, and you got it. Okay? Alright. Keep in mind that for number 18, for example, this is not applicable because I'm not dividing by x minus a constant. I'm dividing by a second degree polynomial. This only holds when you are dividing by a first degree polynomial with coefficient 1. Okay? When you are dividing by x minus c. Okay? So again, this is the theorem. If you are dividing by x minus c, then the remainder is going to be p, the polynomial, evaluated at this number c. Okay? Alright, let's take an example. That's on page 280. Let's do number 40. So let's take this problem with us. So the question reads as follows. Given a polynomial f of x, the quotient f of x over x minus 2 has a remainder of 12. What is the value of f of 2? Well, clearly the remainder theorem here is applicable. Why? Because you have a polynomial, f of x, which is playing the role of p of x here, that's gonna be divided by x minus 2, right? So you're gonna divide f of x by x minus 2. If you perform that, correct, you're gonna get a remainder, and according to the remainder theorem, that remainder is gonna be f of that number, right? F of that number, right? Who's playing the role of c here? X minus c is actually, the c is 2, right? So the remainder by the remainder theorem is f of that value 2. So who's that remainder then? F of 2. That's the remainder. Correct? So that's the remainder by the remainder theorem we just discussed above. So, and then they're asking us, what's the value of f of 2? Well, f of 2 is the remainder, and if you know what the remainder is, which is 12, then that's f of 2. Correct? So f of 2 is equal to 12. It's a very straightforward application of the theorem. Alright, let's do another one. How about 42 now? Alright, so in 42, what do we have? So we have a polynomial, g of x, and we need to evaluate that polynomial g at 2, right? So we need to find, in part A, we need to find g of 2. Alright, so instead of x, I'm going to have a 2. So minus 3 times, every time I see x, I'm going to replace by 2. So 2 to the power 5 plus 2 times 2 to power 4 plus 6 times 2 to power 2 minus x, which is 2, plus 4, right? Every time I saw an x, instead of x, I have it 2 here, okay? All right, so 2 to power 5, that's 32, and 32 times 3 is 96 with a minus sign, okay? 2 times, this is 2 to power 5, so it's 32, right? Plus 4 times 6, 24, minus 2 plus 4. And how much is this? Negative 96 plus 32, that's negative 64. Negative 64 plus 24, that's minus 40. And minus 40 minus 2, that's minus 42. Plus 4, that's minus 38. Correct? So how much is g at 2? That's negative 38. Part B, determine the remainder when g of x is divided by x minus 2. So if you divide g of x, which is the polynomial g of x, by x minus 2, who's the remainder? They're not interested about the quotient or in the process what happened. They're only interested about the remainder. Who's the remainder? Well, by the remainder theorem, if you have a polynomial and you're dividing it by x minus 2, then the value of the remainder is simply p evaluated at 2. In this case, g is p, right? So who's going to be here? That's g of 2. Correct? So the remainder is g of 2. And we just found g of 2. We just found the value of g of 2. How much was it? It was negative 38. So this is actually negative 38 without doing the steps in between. So the question, determine the remainder. The remainder is, g of 2, which was found in part A. So by part A, this is negative 38. Okay? All right. Let's now define what we mean by a zero or a root of a polynomial. So let's read the following definition. Let p be a polynomial and m be a real number. M is said to be a zero or a root of p provided if you evaluate p at the number m, you get 0. So one more time, what's a zero or a root of a polynomial? It's a number so that if you evaluate the polynomial at this number, you get the output 0. Okay? So m may not be 0 itself. It may not be the number 0, m, right? The guy who sits here. It may not be the number 0, but it's called 0 of a polynomial or a root of a polynomial, provided its output is 0. The output is 0, not the input, okay? So m itself may not be the 0 number, but its output should be the 0 value, okay? The output through the function p. So what are the zeros of a polynomial? They are the numbers that solve the equation p of x equals 0, right? This would be the algebraic property. So any number that solves the equation p of x equals 0 is called the zero or a zero of a polynomial or a root of a polynomial. And geometrically, this is where at those numbers, at those roots or at those zeros, the function p crosses the x-axis, right? These are the x-intercepts, correct? So this at those numbers, at those values, at those zeros, the function has x-intercepts there, right? Because the value of the function is 0 there. Okay, so hence the comment here. So let's read the comment. The zeros of a polynomial p are the solutions of the equation p of x equals 0. And if p of m is equal to 0, then the graph of p has an x-intercept at x equals m. Because if this is the function p, then at this point m comma p of m, if p of m is 0, then m comma 0, which means a point on the x-axis, right? A point on the x-axis is going to be at the same time a point on the x-axis and a point on the function p, on the graph of the function p. And such a thing is called x-intercept. Remember that? So, so geometrically, those numbers x equals m, at those numbers we have x-intercepts. Okay, so the x-intercepts of the graph are the zeros of the function. Okay, all right, let's take an example. This is still on page 280, and now let's do, let's say number 50. So what's the question? The question is, use the remainder theorem. What's the remainder theorem again? It's the theorem that we discussed just a few minutes earlier. So it's that theorem, which states if the polynomial p of x is divided by x minus c, where c is a pure constant, then the remainder is the value p of c, right? So we're going to use that to determine if the given number c, the number c that's discussed here, we have two parts. One time c is -3 and one time c is negative square root of 10, is a zero of the polynomial. So the polynomial here is labeled as q of x. Okay? So we want to determine if it's zero. What's a zero again of a polynomial? It's a number so that you evaluate the polynomial at, you get the output 0. Okay? So let's paste that number here. This is number 50. So we want to use the remainder theorem to determine if c, in each case, in part A and in part B, we want to find if this is a zero of the polynomial. So technically the question in either part, let's say in part A, the question is q of -3 equal to 0. That's the question, right? But I don't want us to find it by evaluating the function at -3. They want us to use the remainder theorem, which means we're going to do long division, right? So we have q of x, we're going to divide it by x minus the number c, and we know that the remainder here is going to be, we know that it's going to be q of that c, right? So this is for parts A and B. And in the first case, c is -3, so you're dividing it by x minus the c, which is -3, right? Okay, so I know at the end I'm gonna get q of -3, the desired thing, but they don't want us to evaluate q at -3. They want us actually to do it the long way. Okay, and that's the question. So let's do that. So I'm gonna divide q of x by x minus the -3, and x minus the -3 is x plus 3, right? And what's q of x here? Q of x is 3x cubed plus x squared minus 30x minus 10. Okay? Alright, so we're going to do a long division, and I know that what I get at the end is q of -3. Alright, let's do that. So I want to this is already arranged in a descending fashion for exponents, likewise here. So let's start this process. So x times what is 3x cubed? That's 3x squared. So 3x squared times x is 3x cubed. And if you subtract, oh, I forgot to multiply 3x squared times 3, right? 3x squared times 3 is 9x squared. Now if you subtract 3x cubed minus itself, that's 0. And x squared minus 9x squared, so x squared minus 9x squared is -8x squared minus the 30x minus 10. Alright, let's do it again. Want to multiply x with to get -8x squared, that's -8x. -8x times x is -8x squared, and -8x times 3 is -24x. And I'm subtracting the bottom from the top. This minus itself gone. Minus 30x plus 24x, that's -6x minus the 10, right? Minus the 10. Okay, one more time. I need to multiply x with to get -6x. So that's going to be -6. -6 times x is -6x. And -6 times 3, that's -18. If you subtract, this minus itself is 0. -10 plus 18, that's plus 8, right? Who's that guy then? Who's that guy? This guy is the remainder, which is q of negative 3, right? Q of negative 3. Because I'm dividing by x minus the minus 3, remember? So the remainder must be q of that number, or q evaluated at that number. Okay, so don't forget, what was the question? The question was, use the remainder theorem to determine if the given number c is a 0 of the polynomial. So they wanted to know if the number negative 3 is a 0 of the polynomial. What's a 0 again of a polynomial? A 0 is a number so that you plug it in and the function, the polynomial, you get the output 0. So if we plug in negative 3 in this function, do we get 0? They wanted us to do it this way, and it happens that if you actually plug in negative 3 in the function q, you're gonna get 8, which is not 0, and hence negative 3 is not a 0 or a root of the polynomial q, right? So since q of negative 3 is not 0, it's 8, it's not 0, we infer that. So we infer that negative 3 is not a 0 or a root of the polynomial q of x, right? Because it doesn't verify the definition of being a root, right? Okay. For part B, now I have c to be negative square root of 10. So I'm going to divide now the polynomial q of x by x minus the c, which is negative square root of 10. So I'm going to divide by x minus the minus square root of 10, which means I'm going to divide by x plus square root of 10, right? And if I get the remainder to be 0, then negative square root of 10 is going to be a root or a 0 of q. Otherwise, it would not be a root, right? So let's do that. I'm going to copy q of x, and we're going to divide by x plus square root of 10. So we're going to divide this by x plus square root of 10. So technically it should be x minus the c, which is minus square root of 10, but plus minus the minus is plus, so you get x plus square root of 10, right? All right. So this is already arranged in a descending fashion. Likewise here, we're good to go. So x times what is 3x cubed? That's 3x squared, right? 3x squared times x is indeed 3x cubed. And 3x squared times square root of 10, that's 3 square root of 10 x squared, right? 3 times square root of 10 is what it is, so 3 square root of 10 x squared. And now if you subtract, you get this minus itself is 0. X squared minus 3 square root of 10 x squared, so you get 1 minus 3 square root of 10 x squared, like this. So let me clarify, just in case you have a question here. I need to subtract this entity from this entity, correct? So I'm subtracting from x squared this guy, which is 3 square root of 10x squared. Correct? So what I've done is I simply factored out x squared, and here I get 1 minus 3 square root of 10. Correct? If you don't trust that, go back. Distribute the multiplication over subtraction. 1 times x squared is x squared, and negative 3 square root of 10 times x squared is that guy, right? Okay, so I just wrote it in this fashion to keep it that as the coefficient of x squared. All right, let's erase this part. And for the last part, I don't have I don't have anything that pertains to x here, so that's gonna be negative 30x and negative 10, right? Okay, let's keep going. Now I'm gonna multiply x with something to get this entity. The numerical part, which is 1 here, I'm gonna multiply 1 by something to get this number, whatever this number is. Well, multiply by this number, right? So multiply by this number. So plus 1 minus 3 square root of 10. And for the x guy, x times what is x squared? This is x. Okay? Alright. Multiply this by this, you get 1 minus 3 square root of 10 times x squared. And if you multiply this guy by square root of 10, what do you obtain? Let's do it on the side. So if you multiply 1 minus 3 square root of 10 x, I'm multiplying it by square root of 10, right? So multiply this guy by square root of 10. Let's do it this way. Square root of 10 times 1, how much? Square root of 10 times 1 is square root of 10 minus square root of 10 times 3 square root of 10. Well, square root of 10 times square root of 10 is 10, right? So if this guy gets multiplied by this guy, this is a 10, because the square undoes the action of squaring, taking the square root, right? So square root of 10 times square root of 10, that's a 10, times the 3, that's a 30, right? So that's a 30 x, correct? So we needed this when we multiplied this by square root of 10, and I'm gonna just copy it. So it's plus square root of 10 minus 30 x. I cannot simplify it any further. It is what it is. Square root of 10 is an irrational number, so I cannot subtract. I can subtract 30, but I don't have. I don't know exactly what square root of 10 is, right? So it's an irrational number, which means it's a number so that the decimal point do not have a pattern, and they don't have. It's not a finite number of decimal digits. So I have infinitely many numbers in the decimal digits for this number, and there's no pattern. So it is what it is again. So square root of 10 minus 30 is itself. All right. Let's erase this part. And then what do? We subtract the blue from the green, right? So this minus itself is 0. For the x part, I have negative 30x minus this piece. So I have the green part. Let me do it here on the side. Minus 30x, that's the green guy, minus this blue guy, right? The x guy. This is the x, this is the x. So I'm going to subtract the blue guy from that green part. So minus square root of 10 minus 30x. Correct? Let's do that. What do we obtain here? Let's destroy the parentheses. So minus 30x minus square root of 10 minus square root of 10 x, right? X plus 30x. Agree with that? So technically I did two steps combined in one here. So technically I multiplied this with this, and then I injected the minus. So minus square root of 10x, and I did a similar game when I had the 30 and the x. That 30x minus the minus is plus 30x, right? Very good. So this and this, they're gone. You're only left with negative square root of 10x. So let's copy that. Negative square root of 10x. And then there's this green innocent constant, so minus 10. Because I don't have a constant here, right? So I'm going to just drop it. All right. Okay, so almost there. I still have one step. This is of degree 1, this is of degree 1. So one more time, it puts me at degree 0. And same question, I need to multiply x with, to get negative square root of 10x. So this should be negative square root of 10. Negative square root of 10x times, sorry, negative square root of 10 times x. This is negative square root of 10x. And negative square root of 10 times square root of 10. Well, square root of 10 times square root of 10 is square root of 10 squared. So it's going to be square root of 100, which means 10, right? With a minus sign. With a minus sign. Minus times plus is minus. All right, and I'm subtracting the pink from the blue. Well, they are the same. So you're going to get 0. You're going to get this 0, right? So what's this 0? According to the remainder theorem, this guy is actually this guy, evaluated at negative square root of 10, the c, right? The c, x minus c, x minus the c, square root of 10, negative square root of 10. So the remainder is q evaluated at that. Is this, so negative square root of 10, is it a 0 of q? Is it a 0 of q? What does 0 mean again? Or root? It means that if you plug in that number in the function q, you should get a 0 as an output. And because of the remainder theorem, I know that this value 0 is q of negative square root of 10, and hence negative square root of 10 is a 0 or a root of the function q. So for part B, this is part B. So for part B, I'm gonna technically say the same thing, but this time in the affirmative. So since q of negative square root of 10 is equal to 0, we infer that negative square root of 10 is a 0 or a root. So it's a root or a 0 of the polynomial q, right? Okay. All right. Let's now go back to the remainder theorem. So let's read it again. If the polynomial p of x is divided by x minus c, where c is a pure real number, is a real number, then the remainder is the value p of c. Correct? So what if I tell you that if c is a 0 or a root of p of x, what can you conclude? If c is a 0 of p of x, what can you conclude when you divide by x minus c? You conclude that the remainder must be 0, right? One more time. If c is a 0 of p of x, which means p of c is 0, right? This is what this means. P of c is 0. And what's p of c according to the remainder theorem? P of c is the remainder if you divide x minus c, if you divide p of x by x minus c. Correct? So what can you say then? If c is a 0 or a root of p of x, then when you divide p of x by x minus c, you're going to get a 0 as a remainder. You're going to get a 0 as a remainder. And as such, what do we say about p of x? We say that p of x is a multiple of x minus c, or we say that x minus c is a divisor of p of x. Correct? Remember when you used to divide, like 10 divided by 2, it's 5 and the remainder is 0, right? When you get the remainder 0, what did you used to say? You either say 10 is a multiple of 2, or 2 is a divisor of 10, right? Or 2 is a factor of 10. Correct? So similarly, I'm trying to adopt this terminology here. If I divide p of x by x minus c, and I know that if I know that c is a 0 of p of x, which means p of c is equal to 0, then the remainder, which is by the remainder theorem, which is p of c, if I'm assuming that c is a 0 of the polynomial p of x, I'm assuming then that p of c is 0, then p of x is going to be a multiple of x minus c, or equivalently, x minus c is a divisor of p of x, because I get a clean remainder, which is 0, right? So anytime we have a remainder 0, we say that this divisor is, or divides, or is a factor of this dividend, right? Okay, so if c is a 0 or a root of p of x, then, according to what we just discussed, then x minus c is a divisor of p, right? Of p, correct? Now, if you go backwards, now if you know that x minus c is a divisor of p, which means you know that the remainder is 0. And who's the remainder by the remainder theorem? It's the p of c. So what do you get? If you assume that x minus c is a divisor of p, you get that p of c is equal to 0, which means that c is a 0 or a root of p. So you get this equivalence, right? Equivalence means that it's a two-way street. This implies that, and this implies that. So it's a two-way street. So you get this equivalence between the two statements. And that statement, this equivalence, is called the factor theorem, which is over here. Let's read it together. If p is a polynomial and m is some real number, then m is a 0 of p. So m is a 0 of p, which means p of m is equal to 0. If and only if, this is the double arrow thing, if and only if x minus this number is a divisor or a factor of the polynomial p of x. Okay, so this is called the factor theorem. Let's do an example to apply the factor theorem. This is still on page 280. Let's do number 60. The question here is, use the factor theorem to determine if the given binomial, it's a polynomial which has two terms, right? For example, x minus 2 is a binomial because it's a polynomial which has two terms, and x minus 3 square root of 2 is a binomial because it's a polynomial which has two terms. Anyway, so if the given binomial is a factor of f of x, okay? So we want to determine if the given binomial is a factor of f of x. So let's copy that, or let's paste it. So I want to know if this guy is a factor of that. So clearly we're kind of talking about this type of result. X minus m is a factor or a divisor of a function or a polynomial p of x, in this case f of x, if and only if, so instead of checking this, which means instead of taking f of x and dividing by x minus 2 and checking if you get the result, the remainder 0, you do long division. Instead of doing all of that, which takes time, it suffices, by this equivalence, it suffices to only check if m, which is in this case 2, right, for part A, is 2. It just suffices to check if 2 is a 0 of the function f, correct? So instead of doing long division, I'm gonna just use the factor theorem, and the question becomes, so x minus 2 is a factor of f of x if and only if, right, because of that, if and only if by the factor theorem, so by the factor theorem, so if and only if 2, right, I have here x minus 2 in this context is a factor of f of x if and only if the number m, which is 2, is a 0 of the function f, correct? So if and only if 2 is a 0 of the polynomial f of x. And what does it mean? What does it mean? What does this mean? What does this mean? 2 being a 0 of f of x again. Let's go back to the definition. What does it mean for m to be a 0 of a polynomial? It means that if you evaluate the polynomial at this number, you get the output 0. Correct? So back here, so this means that f of 2 is equal to 0. If I manage to show this, then x minus 2 becomes a factor of f of x. Okay? Let's do that. What's f of 2? What's f of 2? Well, instead of x, I'm going to have 2 here. So 3 times 2 cubed. This is times 2 cubed, sorry. So 2 cubed minus 2 squared minus 54 times 2. What am I doing again? I'm evaluating f at 2. So I'm replacing x by 2. So minus 54 times 2 plus 18. Correct? Let's do that. 3 times 2 cubed is 8. 3 times 8 is 24. Minus 4, right? 2 squared is 4. Minus 54 times 2, that's 108. Plus 18. Correct? And the question, is this 0? Is this 0? I mean, we don't need to do it because it's clearly not 0. Minus 108 minus 4, this is negative 112, and 24 plus 18 is certainly not 112. So certainly this is not 0. You can find the answer, but certainly this is not 0, and as such, 2 is not a 0 or a root of f of x, and hence x minus 2 is not a factor, is not going to be a factor of the function f of x, because f of 2 is not 0. Make sense? So if you actually perform the long division, f of x divided by x minus 2, if you actually go through the trouble of doing the long division, you're going to find here a number which is f of 2, and it's not going to be 0, the remainder. Okay? All right. So as a consequence, x minus 2 does not divide or is not a factor of the polynomial f of x, of the polynomial function f of x, right? By the factor theorem. All right, how about part B? Same thing as part A, but now instead of 2, what do we have? Instead of 2, we have 3 square root of 2. Correct? So technically it's the same discussion, but instead of the 2, I'm going to inject 3 square root of 2. So part B, x minus 3 square root of 2 is a factor of f of x if and only if, so if and only if, based on the factor theorem. So by the factor theorem, f of 3 square root of 2 is equal to 0, which means 3 square root of 2 is a 0 or a root of the function or the polynomial f, right? All right, let's check f of 3 square root of 2. So, in fact, what's f of 3 square root of 2? Well, what's f of x? F of x was 3x cubed minus x squared minus 54x plus 18, right? Let's actually paste it here just to be able to plug in the x. So who's the x again? In this case, it's 3 square root of 2, right? That's what's going to take the role of x, and hence I'm going to see it here, here, and here. All right, let's do that. So I'm going to have 3 times the cube of my x, which is 3 square root of 2, right? Minus the square of my x. And who's my x again? 3 square root of 2. Minus 54 times 3 square root of 2 plus 18. Correct? So I don't need this anymore. All right, let's evaluate this. What is that? This is equal to, let's keep that 3 outside, times, how about this? How about this guy? Let's do it together. This is equal to, actually, how about I do this part before? How about I do this part? Why I'm doing this part? Because that guy is this times one more, 3 square root of 2. Let's actually find this. What is that? 3 square root of 2 squared, which means 3 square root of 2 times itself. Well, 3 times 3 is 9, right? And 9 times square root of 2 times itself. What's square root of 2 times itself? It's square root of 4, which is 2. Correct? So this is 18 then. So this guy is 18. One more time. 3 square root of 2 times itself. 3 square root of 2 times itself. Well, 3 times 3 is 9. And square root of 2 times square root of 2 is 2. And 2 times 9 is 18. This is what I said. Okay? All right. Now, how about this guy then? How about this guy? Well, it's this guy because I have cube, right? It means this guy squared times one more 3 square root of 2. Agree with that? So this is equal to 3 square root of 2 squared times 3 square root of 2, right? I have 3 copies of 3 square root of 2 this time. I piled up 2 because I have a result for that. This is 18. This is 18. Let's do it here. So 18, this guy is 18, times 3 square root of 2. Do you agree with me? So now the question is, what's 18 times 3? Well, 18 times 3 is 54, right? Square root of 2. So the value of this bubble is 54 square root of 2. Alright, so back here now. 3 times the blue guy, which is 54 square root of 2, minus the pink guy, which was 18, minus, let's go back to the green, minus 54 times 3, right? 54 times 3 is 162 square root of 2 plus the 18. Correct? Actually, let's not do this. So let's keep it 54 times 3 square root of 2. All right. And then what? The negative 18 plus 18, those are gone. And 3 times 54 square root of 2 and minus 54 times 3 square root of 2, it's the same thing, right? This number and this number is the same, whatever it is. We know that it's 162, but it doesn't matter. It's the same number. So that number of square root of 2 minus the same number of square root of 2, they're gone, right? So this and this are gone. So what are we left with? 0. So we're left with 0. What does it mean? This doesn't look like 0. So 0 like this. So what does it mean? It means that f of that numbers, 3 square root of 2, is 0. So that means then 3 square root of 2 is a root of f, and hence by the factor theorem, based on the purple discussion, x minus 3 square root of 2 is a factor of f of x. Correct? So as a consequence then, so as a result, x minus 3 square root of 2 is a factor or a divisor of the function or a polynomial function f of x. So is a factor of the polynomial function f of x. Okay? Alright, so these are two parts that make use of the factor theorem. Alright, let's do another problem. Let's go to page 281 and let's do 66. Let's do this problem 66. Actually, let's do 70. Let's do 70 for that. Okay, so we paste it. Let's read the question. Factor f of x. So they want us to factor the function f of x. What does it mean to factor a polynomial? It means to write it as product of things, right? This is a sum of things. Sum and differences of things. I want to write it as a product. This is what factor, right? This is what factor means. Given that 2 is a 0, what does it mean that 2 is a 0? It means that f of 2, right? This means that f of 2 is equal to 0, right? Correct? So f of 2 is equal to 0. So 2 is a 0 of the function or a root of the function f. According to the factor theorem, because 2 is a 0 of the polynomial f in this case, then x minus 2 is going to be a divisor of f of x. Correct? Then x minus 2 is going to be a divisor of f of x. So which means if you take the function f of x, or the polynomial f of x, and you divide by x minus 2, guaranteed that you're gonna get a remainder 0. By the factor theorem, that's guaranteed, in concert with the remainder theorem, right? The remainder theorem has to do with the factor theorem. So the remainder is guaranteed to be f of 2. This is f of 2 for sure. And since they told us that 2 is 0, they told us then that f of 2 is equal to 0. So they told us that the remainder must be 0. Correct? So let's do that. So let's divide f of x, which is 4x cubed minus 20x squared plus 33x minus 18. Let's divide that by x minus 2. And we know that the remainder is 0, right? Let's do that. So what should I multiply x with to get 4x cubed? Just pay attention that here everything is, all the terms are in a ascending fashion or descending fashion for the exponent. That's good. So the arrangement is good. Likewise here. I'm going to multiply x by something to get 4x cubed. What is that? 4x squared, right? 4x squared. Let's take it down a little bit. So 4x squared. Now 4x squared times x, that's 4x cubed. And 4x squared times negative 2, that's negative 8x squared. Okay? And now we're going to subtract. 4x cubed minus 4x cubed, that's 0. Negative 20x squared plus 8x squared, that's negative 12x squared. Plus the 33x, I don't have an x term here, and I don't have a constant term here. So I'm going to just drop these in some sense. All right, let's keep going. X times what is negative 12x squared? Well, negative 12x does the job. Negative 12x times x is negative 12x squared. And negative 12x times negative 2, that's plus 24x. Okay, now we subtract. What do we obtain? This minus itself is 0. 33x minus 24x, how much is that? 33 minus 24, that's 9x minus 18. Correct? All right, one more step. We're not there yet. We should have a remainder. It should be a constant because the degree must be smaller than the degree of this, which is 1. But we know that the remainder must be 0, right? They told us this. They told us that the 2 is a 0, which means x minus 2 by the factor theorem is a divisor of f of x. So I should get 0 for sure as a remainder. Hope you see it. If not, let's do it. So x times what is 9x? Well, that's going to be 9, correct? 9 times x is 9x. 9x. And 9 times negative 2 is negative 18, right? And now if you subtract, you see that you get that remainder 0, which is f of 2. Correct? Why this is useful? Why this is useful? Because now I can write this dividend, the f of x, as x minus 2 times this purple guy, right? So now I can do the following. So thus, f of x, which is this guy, right? This is f of x, is equal to x minus 2 times the divisor times the quotient, 4x squared minus 12x plus 9, plus the remainder, which is 0, right? I can erase that. So f of x, which used to be this sum of 4 guys, now I'm writing it as a product. They want to factor, remember? They want to factor. So almost there. I found one of the factors, x minus 2, and then I still need to factor this guy. This is a second degree polynomial. I still need to factor it into linear factors if possible, right? Let's do that. So now, next, we need to factor 4x squared minus 12x plus 9, correct? And here, what are we gonna use? If you don't have any intuition into it, let's use the quadratic formula. So to do this, we use the quadratic formula. Some people see it immediately and some don't. So let's pretend we don't see it and use the quadratic formula for it. So again, if you need to refresh on quadratic formula, go to one of my videos. It's entitled Quadratic Formula. So and just look at that and see what the formula was. I'm gonna just quickly apply it here. So 4x squared minus 12x plus 9, according to the formula, I can write this as 4 times x minus something times x minus another thing. Let's call this guy asterisk, and let's call this guy double asterisk. Where asterisk is equal to minus b minus square root of b squared minus 4ac divided by twice a, and double asterisk is equal to, very close to that, plus square root of b squared minus 4ac divided by 2a. Okay? And this is equal to, the b here, let's be very clear who's a, who's b, who's c. A is 4, a is the coefficient of x squared, b is negative 12, and c is 9. Okay, so those are the ingredients for this quotient. Negative b becomes 12 because negative 12 is 12, minus square root of b squared, that's 144, right? Negative 12 squared is 144, minus 4 times ac. What's ac? 4 times 9 is 36, right? Divided by twice a, and twice a is, because a is 4, twice a is 8, right? Alright, so this is equal to what? This is equal to what? Let's do that like this. So 12 upstairs minus 4 times 36 is 144, right? And minus 144, that's 0, so square root of 0. So we get 12 over 8, which clearly can be simplified a little more. What's 12 over 8? If you simplify by 4, you get 3 over 2, right? So one more time, we simplified here by 4. 12 divided by 4 is 3, 8 divided by 4 is 2. Okay? And double stars, or double asterisk, is actually the same, because the only difference was from here to here is just the minus, between minus and plus, right? But this guy has vanished, so this is 0. So this is also 3 square root of 2, 3 over 2. So this is also 3 over 2. So I'm gonna rewrite, instead of asterisk and double asterisk, it's the same guy in this case. They're both 3 square root of 2. So hence, so it follows that (4x squared minus 12x plus 9) is equal to 4 times x minus 3 over 2 times x minus 3 over 2, right? What did I do here? Instead of asterisk, I put 3 over 2, and instead of double asterisk, I also replaced 3 over 2 because these are the values of those guys. So I get this. So some of you say, oh, we got 2x. I mean, some of you may have seen it immediately here that it's 2x minus 3 squared. Well, that's the same thing that we said here. This is the same thing that we said. Look, the 4, I can think about it as 2 times 2, right? I can think about it as 2 times 2. Times this factor, right? Times this factor. I just shuffled them around because multiplication is commutative, not a big deal, right? That's still 4, that guy. The 4 is coming from the 2, 2. and this guy, right? Okay, and what is that? This is, if you bring in the 2 inside this factor, 2x minus 2 times 3/2 is 3, right? Times the same thing. 2 times x is 2x, and 2 times 3/2 is 3. So that's 2x minus 3 squared. Correct? It's the same guy times itself, so you get the square of that guy. So many people would have seen it immediately from here to here, but if you don't, quadratic formula definitely would be the heavy gun for it, right? Alright, so what do we get? We managed to factor this piece. It's right there. We factored it as such, right? It's right there. So what can we say then? F of x is going to be x minus 2 times this piece. Correct? So it's going to be x minus 2 times this piece. So all in all, f of x is, as we said, x minus 2 times this guy, which is 2x minus 3 squared. Didn't we factor f of x? Yeah, it's a product now of x minus 2, 2x minus 3, and 2x minus 3, right? But it happens that 2x minus 3 is needed twice. Alright, so this is part A. This is the end of the first part. Correct? So this is part A here. This guy. Now, part B. They want us to solve this equation. They want us to solve this equation. And what's this equation? This equation is 4x cubed minus 20x squared plus 33x minus 18. Who's that guy? Who's that guy on the left side of this equation? Who's this guy? Isn't it f of x? Isn't it f of x? This guy is f of x, right? So they want us to solve then f of x is equal to 0. They want us to solve f of x is equal to 0. So which means we need to find all the roots of f. We know one of them is 2, right? We know one of them is 2. The question is we need to find all of them. 2 is going to be among those guys, but we need to find all of them. So I want to solve f of x is equal to 0. That's part B. So part B, I want to find f of x when f of x is equal to 0. And f of x, based on how it was written, it's a sum of things, right? It's a sum of things. Now, if you use part A, the factorization form of f of x, which was this guy, you can replace f of x by this guy. And this is easier to solve it because this is the same as saying x minus 2 times 2x minus 3 squared is equal to 0. What did I do here? I replaced what f of x means, right? This is what f of x means. Let's color it the same thing. This is f of x, the same f of x by part A, right? Why this is useful? Why this is more useful than this one? Remember, f of x was bunch of sums. Well, because I know exactly when a product is 0, right? A product is 0 if and only if at least one of the factors is 0. Correct? So I have 3 factors technically, x minus 2, 2x minus 3, and 2x minus 3. So, but two factors are the same. So when is this product 0 then? This happens exactly either when x minus 2 is 0, right? If this guy is 0, then the product is 0, isn't it? Or if 2x minus 3 is 0. Does it make sense? So a product of things is 0. In this case, I have 1, 2, and the third one is the same as 2x minus 3. So a product of things is 0 if and only if at least one of the factors is 0. And I have x minus 2 as one factor and 2x minus 3 as the other factor. I have a third one which is the same as the second one. Okay, so I'm going to just write it one time instead of writing or 2x minus 3 is equal to 0 for the third factor. But this is redundant here, so I'm not going to write it. Okay, so then f of x is 0 if and only if this happens, and this is an easy equation, right? When does this happen? When is x minus 2 0? It's when x is 2, right? By adding 2 here to both sides. And how about that? When is 2x minus 3 0? Isn't it when x is equal to 3 halves? Just add 3 and divide by 2 here, you get this. These are the asterisk and the double asterisk we found. So f of x is 0 then if and only if this happens. Either x is 2 or x is 3 over 2. So the solution set, thus the solution set of the equation f of x equals 0 is just the set consisting of 3 halves and 2, right? These are the only two values for x, so that if you plug them back in x in the function f of x, the output is going to be 0. We knew 2 is going to be there, right? We knew that 2 is going to be there. It's part of the first part, correct? They told us that 2 is 0. They told us that 2 solves the equation f of x equals 0. So they told us this. The question is, they wanted all of them, and the only missing one was 3 over 2 other than the 2. Okay? So this function f of x has two roots, 3 halves and 2. Okay? Alright, so by this I'm ending this section right here.